So let's look at how we can calculate meaningful change in test scores. So the athlete's been tested at these various time points. These are the trials that we've collected for the test so that we can look at reliability. And of course, we take the best score as it's a capability test. In this example, jump height. So the question we'll look at here is, has the athlete improved from test to test? So we're only comparing the current test to the previous test. In the next video, we'll look at how we can anchor that test to a fixed baseline, or indeed to the start of a block, and why that's important, as well as how to generate a graph so that you can look at the trend as well as the signal to noise ratio and whether those changes are meaningful. So how do we calculate this meaningful change? Well, first what we have to do, of course, is calculate the improvement in performance. So here, for example, we have an improvement where we go from 33.1 centimeters, which is the current score, and the previous test was 29.9 centimeters. So the improvement is 3.2 centimeters. But of course, whenever you test, there's always error. And in this example, we have two testing points, so two sets of error that we have to combine. And what we want to know then is that improvement greater than the error that we would expect to see, or the noise that we would expect to see, had there been no performance improvement in the athlete. And so we therefore have to combine the two sets of error, which are represented by the standard deviation from both sets. So what we do, which is called propagation and variance, is we square the two standard deviations, we add them together, and then we take the square root. So the error is 1.3 centimeters. Now, when we divide the change in performance by the error, we get this standardized score. And what the standardized score is saying is that improvement in performance is 2.5 times greater than what we'd expect to see just from error. So we can be confident that this change is indeed real. So let's just look through this with respect to this sheet here. So again, we've got the best score from those 3 trials, the standard deviation from the 3 trials here. And what we want to do now, again, is compare the current score to the previous score. So again, it's 3.2 centimeters. Combine the noise. So we square the standard deviation from one test, add it to the squared standard deviation from the other test. Keep that in brackets, so that happens first, and then we take the square root, and there's our 1.3 centimeters. And now we just divide the change by the noise to get our noise scale change. Again, because it's such a large change, we can be very confident that that change is indeed real. Had it just crept past, or say like 1.3, that's still a very much so a likely change. But because it's just a bit bigger than the error, we might have less confidence in that change. So we say likely better. As soon as we're breaching double, now we're starting to say, yeah, that's a very meaningful change. And you can use whatever descriptors you like, and you can change the terminology here using this formula.